So today what I'd like to do is that I'd like to go over the next couple of classes. We're going to look at convolutional neural networks because I think that these are probably the most successful models that people are using in image recognition, in speech as well. So these are, in medical images, anything that has to do a 2D structure. These models are the state of the art. How many of you have heard about convolutional neural networks? Okay, so probably most of you. How many of you ever trained a convolutional neural network model? How many of you actually implemented backprop for convolutional neural network? Okay, a few. Okay, so that's good. So hopefully the goal of today's lecture, and again of your homework, is that you'll start understanding better how these models are working, right? Obviously in today's world, you have TensorFlow, PyTorch, and everything is pre-computed for you. But it's important for you to understand, ideas behind these models so that you can invent new architectures, new optimization algorithms. And also when you go on the job market, they ask you, like, have you done convolutional neural networks? And you say, yes, I open TensorFlow, I specify the layers, and I specify convolutions, and this is the answer I get. So, typically there's going to be lots of people who do that, obviously, because that's now more of a technology. But again, if you're looking for jobs that relate to as computer vision, you have to know these models inside out. Okay, so these are some good resources. As I mentioned, there is a Hugo's class on neural networks. A lot of material is going to be borrowed from his class. There's going to be some tutorials that are going to be borrowed from Rob Fergus's tutorial. And some slides are also going to be borrowed from Mark Aurelio from CVPR. So Hugo is at Google, Rob Fergus is at Facebook, and Mark Aurelio, I believe, also at Facebook. Right? So pretty much heavy industry oriented folks who kind of using these models. Okay, so what is computer vision? You want to design algorithms that process visual data to accomplish a particular task, right? So for example, in object recognition, what we're trying to do is that we're trying to take high-dimensional image and classify, right? Or specify which object it contains. So the goal for this class is going to be to look at or design these neural networks that are specifically adapted for these problems. Now, typically, when we go in the domain of vision, we have to deal with very high-dimensional inputs, right? So, for example, if you have an image 150 pixels by 150 pixels, which is considered to be small image, right? You have plus 3 channels, RGB. You have tons of pixels to deal with, right? In real world, when you work with like high-resolution images, a million pixel by million pixels, or if you look at medical images, the scans, these are even higher dimensional, right? You have 4,000 by 4,000. These are high-resolution images, and typically you're going to be looking for small patterns in those images. It becomes tough, right? And so you have to be able to exploit 2D topology of pixels, or in many cases, if you're working with the video data, sequential data, you have to be able to explore 3D topology for the video data, right? These pixels are not just random perturbations. I mean, they have spatial correlations. So the goal for us is going to be to exploit that. And then the other idea is that you want to be able to build invariances to certain variations. So variation in translation, for example, right? If I show you an image and I take the same object and move it 5 pixels to the right, you still want to say it's the same object, right? And that's something that we can use as a prior knowledge. So convolutional neural networks really rely on the prior knowledge that if you see my face and my face moves 2 pixels to the right, it's still going to be my face. So it's invariance of features in different locations of the image. And also things like illumination and such, you want to incorporate that. So convolutional neural networks leverage these ideas, and they do it by using, I guess in this case, 4 different concepts. One is local connectivity. Second is parameter sharing. Third is convolution. And fourth one is pooling and some sampling, right? So we'll see some of these examples. although pooling and subsampling in the last couple of years, people actually learn what the right pooling should be instead of actually doing max pooling. Right? Like if you look at more recent architectures that we're going to look at in the next class, like residual networks, those networks don't actually have explicit pooling, but you're actually learning what these pooling functions should be. But nonetheless, we're going to go through all of these 4 different concepts. So let's look at the local connectivity. What you'd like to do is you'd like to use the local connectivity of hidden units. So for example, in your homework right now, every single pixel is connected to all hidden units, right? So this would be a fully connected neural net. But in this case, each hidden unit is going to be connected to only a subregion or a particular part of the input, right? So R here is going to be the receptive field. So this is sometimes called receptive field. All these pixels in this region are connected to the hidden units. And all the pixels in this region are connected to this hidden unit, right? So if it's connected to all channels, 1 if it's grayscale, or 3, you have 3 different channels. So why would you want to have local connectivity? And the idea is fairly simple, right? Fully connected layers, they have a lot of parameters. So it's just impossible to, deal with high-resolution images. You have to restrict connectivity. And then the more important piece is that the spatial correlation is local. What's happening here might not impact what's happening here, right? In particular, looking at the local correlations. Yes?
Is this local connectivity only for the first hidden layer, or do you do this in the other hidden layers?
Yeah, we'll get to that. So, but let's look at the first hidden layer. So the first hidden layer, you have this local connectivity, right? Saving on the number of parameters. And again, the assumption is that, there is spatial correlation. So things in this region are correlated, but might not be correlated across, different parts of the image. So units are connected to all the layers. And again, if you think about representing images as 3 channels, then you have a receptive field here, receptive field here, receptive field here, and they're all connected to this hidden unit, right? All these guys are connected to this hidden unit. Okay? Now, here's an example of a local connectivity. So you have a 200 by 200 image, and you have 40,000 hidden units. Let's say you have 40,000 hidden units, then you would have about 2 billion parameters, right, to fit. So 2 billion parameters basically you can't really fit. But the spatial correlation is local, and it's too many parameters. In fact, there aren't any sort of successful algorithms where you can use fully connected models, particularly for images, that work as well as convolutional neural networks. So ConvNets work almost always, I shouldn't say always, but almost always better than fully connected models, right? And this is an example of, if you have 40,000 units, but the filter size is 10 by 10, so they only connected to 10 by 10 pixels at different locations, you'd only require 4 million parameters, right? So you go from 2 billion to 4 million parameters because of the spatial, because this local connectivity. Now, this particular parameterization is good when the input is registered, right? Because if this feature here is looking for an eye, and now I take my face and move it to the right, then this feature is no longer going to be detecting an eye. Right. So this particular parameterization only is good when your input is fixed and registered, if I'm looking at the faces. Yes?
What does registered mean?
Registered basically means that your eyes, or a particular object that you're trying to recognize, is at exactly the same location for all the images. So for example, when people look at fMRI scans, they look at they study the properties of the brain and the voxels that you see in the brain. These are fMRI scans. Most of those images are highly registered. They have exact same location for all the images. But in practice, this we have to deal with this because there's a lot of variations. I can move my head and it's not quite at exactly the same location, so we'll have to deal with that. Let's look at parameter sharing. So parameter sharing is another idea that was introduced in the early 90s. I think it was by Jan LeCun, to share the matrix of parameters across hidden units. Okay? So what you want to do is you want to basically say units, hidden units, are going to be organized into the feature map. And units within the same feature map are going to be sharing parameters. Okay? So they're just replications. And hidden units within a feature map cover different positions in the image. So let's look at that. In this particular example, this is feature map 1, but it has, let's say we look at these 3 different receptive fields. The parameters here are shared, right? So I'm using the same parameters to extract features here, to extract features here, and to extract features here. That's one feature map. This is a second feature map. It's looking at the same receptive fields, but it has different parameters. And you look at feature map number 3, again, same feature maps, but different parameters. Okay? So what's going on here? Imagine that these particular features here, what they do is they detecting an edge. Let's say a vertical line. So you want to detect vertical lines in your image. What this parameterization is doing is that whether the vertical line happens here or here or here, you use the same detector. So it's almost like running the detector across the entire image if you're detecting, vertical line. And the inductive bias that these models have is that images are translation invariant. So detecting a vertical line in this part of the image is, equivalently detecting it here or here. And then this feature map might be detecting a different edge, right? It might be detecting a horizontal line. These features might be detecting certain, pattern in the color, right? So you have these different feature maps, and each one of them, again, you can think of as a small detector that runs across the image and detects one particular activity. Okay? So same color, the same matrix of connection, and Wij here is the metric connecting ith input channel with the jth feature map, right? So that's the basic basic notion behind convolutional neural nets: local connectivity and sharing of parameters. And if you think about this, it's actually pretty clever. Because if I have 10 by 10, if I'm looking at 10 by 10 feature map, then effectively I'm going to be learning 100 parameters, right? Because this matrix here is going to be of size 10 by 10, is going to have 100 numbers. But now this is also going to have the same 100 numbers. This is going to be the same 100 numbers. This is going to be another 100 numbers, another 100 numbers. So this entire model is only learning 300 parameters. Right? But I'm looking at different parts of the input, and I'm actually trying to detect different edges. Okay? So there's a drastic reduction on the number of parameters, precisely because you're sharing parameters across different locations. There's a question?
No, just you have to define a priori condition, the same color.
Yeah, the same color means the same matrix of connections, and the same parameters. The what?
The model discovers that condition, or
yeah, that's the condition in the model. That's you implicitly say in the model, right? These parameters are shared. So why do you want to share the parameters? It even reduces more the number of parameters, and what it does, as I mentioned before, it's extracting the same features at every location. So the features are equivariant. Okay? So think of it, if I have a feature for an eye, then an eye could appear anywhere in the image, right? In principle, when I take a picture. And so I'm just detecting one particular feature. So when you look at convolutional neural networks in general, we're going to go through convolution, most of the compute happens here. The first layer and the second layer, because you can create 20 different feature maps. They all share the parameters. The number of parameters you're learning is actually pretty small. So it's kind of funny that you use a lot of compute to detect certain patterns, certain features, but the number of parameters is fairly small. And so you share the same, so what you can do is you can share matrix of parameters across certain units. So here you're sharing it. And this would correspond to convolutions with certain kernels. Okay, so this operation, when you're sharing the parameters and you're kind of like using a sliding window of applying, multiplying this region with the weights, multiplying this region with the weights, multiplying this region with the weights, and so forth, that's operation is called convolution. Okay? Any questions? So let's look at the definition of the convolution. It's also pretty straightforward. So each feature map would form a 2D grid of features, right? Because you're working with 2D images. And if you want to extend into 3D images, those would be a 3D convolutional, 3D feature maps. So sometimes people take time as a third, dimension, or if you're working with, multi-dimensional images and such, you can extend that. So here you have an input image. You have 4 different feature maps because you apply the same convolution at every single layer. So it can be computed with a discrete convolution of a kernel matrix K, which is a hidden weights matrix W. So think of the kernel matrix as your weight matrix W that you're trying to learn, with its rows and columns flipped. It's just by definition of convolution. So here, you take your X, which is your input. You have your kernel, which are your weights that you're trying to learn. But by definition of convolution, you apply convolution to the image at all locations, at all positions of the image. You pass it through nonlinearity, and then maybe you scale it up by some other factor, and that's the output, right? So X is the ith channel of the input, Kij is the convolutional kernel. And again, when we do convolutional neural networks, we're going to be learning what these Ks are. These are essentially the parameters, the weight matrices. G is sometimes called the learning scaling factor. In many cases, you can extend it, what the scale of it should be. In many cases, you just set it to 1, sorry. That doesn't make sense. It should be Yj is the hidden layer. It's the output of the hidden layer. And then you can also add bias to it. Okay? So let's look at definition of the convolution. So the convolution of an image X and a kernel K is computed as follows, right? And probably you've looked at convolutions before if you've taken, the basic math classes or the basic statistics classes, right? How many of you have seen convolutions before? Okay, many of you. In a discrete space, it really is just this equation, all right? Let me give you an example. Sometimes it's easier to look at the example. If this is my X and I want to convolve it with K, what do? I take this matrix, I flip it, and I multiply it to these 4 numbers, right? That's the definition of the convolution. So in this case, you say 1 times 0, 0.5 times 80, 0.25 times 20, there is a 20 here, 0 times 40. You add it up, you get a number 45. And then again, you convolve it here, you get 110, you convolve it here, you convolve it here, right? So at the end of the day, in discrete space, you just have a small matrix, you have a large matrix, and you're just multiplying across, all the rows. So you're multiplying here, 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 here. And that's a convolution. Yes?
Why did you have to flip it? Is that just definition?
That's the definition of the convolution. So it's just to be consistent when if you look at the definition of the convolution, that's how it's typically defined. Now, for convolutional neural networks, what we're going to be doing is we're actually going to be learning what that filter is, right? These are going to be the weights of the model. So you don't really have to flip or do anything, right? You just basically say, these are my weights, and I just multiply my weights across the image, and I get my feature map. And that would be my feature map, right? That would be the response of the convolution. So how can it be computed? So the pre-activations from channel Xi, in case we're working with RGB images from a particular channel, into a feature map Yi or Yj can be computed by getting the convolutional kernel, which is the transpose of your parameters, from the connection matrix and then just applying the definition of the convolution. The reason sometimes people use that particular notation, which is W transpose, is because in many cases there are very efficient libraries where you can say convolve this matrix with this matrix, right? And people have worked a lot on, coming up with the right, like very efficient libraries that compute that. So for example, many of you who are familiar with CUDA libraries, the GPU libraries, there was a whole team of people trying to optimize for these convolutions, right down at, a low level. There's also an interesting story. This now forms this particular convolution. So here's an example of, I give you an image, 0 to 225, and I take my W, which is the W transpose in this case, and I just convolve this matrix with this matrix, right? So I convolve it, and this is the output of the convolution, right? So it's just a matrix-matrix multiplication. If you look at a lot of deep learning models and convolutional neural networks, this is the most expensive operation when I work with large-scale images. And if you try to build a system that can do it in real time, you have to be very efficient, right? You have to take into account zeros and so forth. And then when you're building these models that have 20 layers, so you do convolution, and then you do convolution over convolution, you do convolution over convolution over convolution, right? So you're building all of these models, and they're the state-of-the-art models. How you actually use this operation is a big deal. In fact, there was a company called, I think it was called Nirvana, that basically got a bunch of people, and they were working on a software to increase this multiplication, right? Really going down to the level of GPU computing so that they can run it faster, right? And then a couple of years down the road, they sold the company to Intel for $100 million, right? So here's a story for you. If you can figure out how to multiply the matrix by matrix, and you can do it better than anyone else, there is a market for it, which is quite interesting. So there is a lot of, if you've heard about latest units coming out of GPU, from Google, TPUs, a lot of it is done on how can you do this operation as efficiently as possible, right? It's a matter of whether you can have a real-time system that detects objects versus not having it in real time, right? So with nonlinearity, now what you can do is that, let's say you take your feature map, you pass it through nonlinearity. Sometimes if you want, you can scale it up, you can add the bias. This is the most general form. You get some nonlinearity, you have a nonlinear, and this is your feature detector at the first layer. Okay? So that's what you get. That's the basic building block of a convolutional neural network. In many cases, you can use zero padding to allow going over the borders, right? So sometimes if you try to apply like 10 by 10, 10 by 10 filter, you sort of can't really go over, so you can pad it by zeros. That's a commonly used technique, right? So you can apply it to the bigger images. And then you get this convolution. Here's an example of, if you take this image and you convolve it, and again, it's a big matrix, grayscale numbers. If you convolve it with this matrix, then if you think about this matrix, it kind of looks like this. It really is looking at the boundaries, going from -1 to 1, kind of like going from black to white, if you think of it that way. If you convolve it, you get this representation. So you can see it sort of finds edges. Like at the lower level, it really like whenever there are edges, the model is discovering those edges. And in many cases, this could be a good representation because it can tell you something about, kind of that it could be a forest because there are so many edges in this image. Any questions?
What all hybrid parameters will be specified?
Yeah, we'll get to that. We'll get to that. So, and again, what you want to do is, there's a question? Go ahead, yeah.
You said that parameter sharing will restrict the same feature at every position.
Yes.
In that sentence, what is the position here? On the feature or the feature map?
So if you think about, so let me go here. This is your image, right? And you apply, 2x2 filter. And let's say this 2x2 filter here, it's kind of like detecting checkerboard pattern, right? So if you look at the output, it has this number, it's quite large. So it basically means that for this number, when you apply the filter over here, it found this checkerboard position because there's 255, 255, 0, 0. So it sort of has a response saying this checkerboard position is quite high here, but it's low everywhere else. So it's position invariant in the sense that you can look at the position here in your feature map, and you can say here in this position I'm finding checkerboard pattern, right? So it's position invariant because it's not like you're saying I'm going to only apply this feature in this region of the image. I'm actually applying it everywhere, right? So it's position invariant detection of the feature, but then the feature map itself specifies the position, right? Because in the feature map, you know where that particular feature occurred. So let's say we have 200 by 200 image. We have 100 filters, and the filter size is 10 by 10. We end up with only 10,000 parameters. Okay. So that's pretty reasonable, right? If you think about 10,000 parameters, in your homework, you're training a model on MNIST, which has like 784 numbers times how many hidden units you're looking at? 100 hidden units, right? So 784 times 100, how many parameters are you fitting? 784, 78,000, right? So your first layer on your homework of a fully connected model has more parameters than this model here, right? So that's why, in many cases, this is a drastic reduction of parameters. And so this is something to keep in mind. It was designed by choice to deal with high-resolution images. And there's been a few papers that actually look at very high-resolution images coming from medical domain, where they've used 5x5 filters and they share the parameters. So computationally, this is much more expensive than what you're doing in your homework, right? In your homework, you just multiply input by matrix, you get the hidden states. Here, it's much more computationally intensive, but it's looking at this spatial local detection of features. Now, let's look at another operation, which is called pooling and subsampling. It's another important operation to keep in mind. So what you'd like to do is you'd like to pool hidden units in the same neighborhood. And pooling is performed in non-overlapping neighborhoods. So sometimes it's called subsampling. So when you read papers, sometimes people would say, yeah, I'm using a pooling layer or a subsampling layer. And the idea is the following. You have some neighborhood, P by Q. So let's look at it. So what's the definition here? Xi is the ith channel of the input. So let's say it's the R channel of the input. Xijk is the value of the ith feature map at position jk, right? P is the vertical index of the local neighborhood. Q is the horizontal index of the local neighborhood. So typically P and Q could be 5 by 5. Or you look at some local neighborhood, typically 2 by 2 or 3 by 3. And what you do is you just take the maximum value. So in this particular example, let's say you look at your feature maps, right? It's performance over feature maps. You look at small neighborhood around, let's say 2 by 2 or 3 by 3, and you pick the maximum value. So the question for you is that, what is it accomplishing? Can you give me an intuition? Why would I do that?
You only look at the most important feature.
That's right. So what you're doing here, let me just, maybe there's a better visualization, but let's look at this feature map. If I look at the small neighborhood over here and I pick the maximum, right, what does it do? Let's say one of my features is detecting my eye, right? If I move my head 2 pixels to the right, the feature that I'm going to detect, its position in my feature map is going to be shifted by 2 pixels, right? And if I use max pooling, then I'm still going to take that there is an eye here, but I'm sort of making it a little bit invariant with respect to the neighborhood, or with respect to the local neighborhood. So the output of the pooling operation will be, if I have my face and I have a feature that detects my eye, if I move my face to the right by a few pixels, the output of the pooling operation is going to be the same. It's just going to say that feature exists somewhere in this neighborhood, right? And that's actually played a fairly important role because it allowed these models to be a little bit translation invariant, right? Yes?
I'm confused about what's achieving the translation variance, because I thought when earlier you were talking about parameter sharing, I thought parameter sharing was doing that because it was the, regardless of where the eye occurred, it's the same parameters, so if it occurs in the next one, it still registers. But now, are both of them together achieving?
Yeah, so both of them, yes, a good question. So both of them are achieving that. But what pooling operation is really achieving is it's basically saying once you pool here, you get another pooling layer, which just basically pools over local neighborhoods. What the model is saying, the model is essentially saying there is an eye in this location, but I don't have to tell you precisely where it is. Right? Whereas if I don't do that, my feature map would contain the position of an eye. So it's basically when you go to the next layer, even if I take my image and I'm slightly shifted to the left, to the right, the output of this layer is not going to change because I'm doing pooling. Right? Now, if I change by a lot, then the output would change. But if I don't change by much, it's not changing. So it really is bringing invariance. And that's an important concept that, that was driving a lot of success of convolutional networks. Sometimes you can also use averaging operation. And the averaging operation is just average the values in some local neighborhood. This doesn't work as well. People have tried doing that. So max pooling is a more common operation. And when you think about hyperparameters, you have to figure out what is it that you want to pool over, what neighborhood you want to pool over. Do you pool over 2 by 2? Do you pool over 3 by 3? And so forth. The other hyperparameter to think about is the size of the feature, is the size of receptive fields, right? When you do convolution, do you do 3 by 3? Do you do 5 by 5? Do you do 10 by 10? Right? When you're applying this convolution on the image, that's another hyperparameter to think about. Depending on different hyperparameters. Another sort of hyperparameter that I haven't really mentioned is when you apply convolution, by definition, you should apply it by something that's called a stride of 1. So you apply it here, then you move 1 pixel to the right, you apply it here, you move 1 pixel to the right, and so forth. But in principle, you don't really have to move by 1 pixel. Maybe you can move by 3 pixels, right? Or you can move by 2 pixels, or you can move by 5 pixels. So these are all design choices that a model has to make, right? Because it's a whole bunch of different architectures. And one particular thing I want to point out for these kinds of models, it actually was quite interesting because for the longest time, if I show you an image, which is 250 by 250, it's a decent size image. What would you think the pooling? Also, what do you think the receptive field should be? Like if you think about like each receptive field is detecting certain features, what's a reasonable size? What's the smallest feature you can detect when I'm detecting horses or dogs or all these different objects in 250 by 250 image? Any guesses? 10 by 10, 10 pixels by 10 pixels, you can see something, right? People try to use 7 by 7. People try to use 15 by 15, right? Seems reasonable, right? This is something that you can detect. And then I think that 4 years ago, at Oxford, there was an ImageNet competition, and at Oxford, the team at Oxford won the competition. And what they did is they basically used a model that used 3 by 3 convolutions. 3 pixels by 3 pixels. Right, which is crazy. Nobody even was thinking about use that. So you do 3 by 3, and then you another layer 3 by 3, another layer 3 by 3. So you go like 3 by 3 all the way, stacking I think like 20 or 30 different layers, just 3 by 3, and it was state-of-the-art model, beat everyone else. So the question is like, what is 3 by 3? Like if you look at 3 by 3 filters, it's like, what can it learn? But it turns out that it's actually doing something interesting. Like it's detecting some small perturbations in pixels, and then the next layer puts them together, and the next layer puts them even more together, right? So it's kind of like the what? They had more layers, but everybody thought that at the first layer, 10 by 10, like nobody would even think to do 2 by 2 or 3 by 3. This is just too small. But they kind of just did it and showed it was one of it's called VGG network, which we're going to talk about in the next class, which actually is right now one of the standard models to use. So sometimes when you look at this model, you look at the intuitions, they can be counterintuitive. But again, the design is something up to designed by the modelers. So this is what the max pooling would look like. If this is your feature map, you look at this neighborhood 2 by 2, 2 by 2, 2 by 2, and just take the maximum. The maximum value here is 0.19, and that's what you get. Right? Pooling also allows you to reduce the size, right, of the feature map. And that's also important. So effectively doing downsampling. So your resolution becomes coarser and coarser as you go up, right? So pooling introduces invariance to local transformation. So it doesn't really matter whether I'm detecting a feature at this location or this location or this location, right? All I'm saying that is in this neighborhood, I'm detecting the feature, right? There's an eye feature here. It also reduces the number of hidden units in a layer. And then, if you think about these pooling operations, at some point they're terrible for generative models, because effectively you're losing the precise position of features. So there's some research trying to figure out, how can you do it probabilistically? Is there probabilistic max pooling or something that we can take into account? Because essentially, if I'm detecting an eye and I lose the location of my eye, and I'm detecting this eye and I slightly lose the location of my eye, then in principle, if I show you a picture of me where my eyes are like 45 degrees related to each other, the model, when it goes up to the highest level, will say, yeah, it's a face, right? I'm detecting eyes, and that's good enough. It's hard, in many cases, it's hard to incorporate some geometric constraints into these models because you're losing precise locations of your features. But it works very well for recognition, right, for detection. Okay, so here's an example of a pooling. Again, you're taking the maximum over the filter size. So typically you have, this is your feature map, and you design some neighborhood. It's a choice. It's precisely what the size of the neighborhood, and then you're getting the pooling. Translation invariance. This is just to illustrate that whenever you do pooling, you have sort of local translation invariance. So what happened here is both of these images will have the exact same feature map. And notice that this image is translated up by 1 pixel. Right? You see that? Well, I think it's translated up, or maybe not. Okay. This part of the input, it's translated up, right? So you can see that this, you move up, this, you move up. And when you look at the feature map designed by both of these images, it's exactly the same. So this translation is happening here. And I think there's some missing piece happening here, but it doesn't really matter, right? So you can introduce some invariance. And indeed, you do some invariance. You can train, if you've played with convolutional neural networks, you can really take the image, translate it a couple of pixels to the right, look at your activations of your higher layer features. They're going to be about the same. In many cases, they're going to be exactly the same. So this is the architecture of what the convolutional networks would look like. You alternate between convolutional layers and pooling layers, right? So let's say you have an image, You have 9 by 9 convolutions. You have sometimes these are called feature maps or kernels. In the 90s, they were called kernels. Today, I guess they're called feature maps. So you create this kind of layer 1 of these convolutions, and then there are 64 feature maps that you're creating, right? And then you're doing pooling, so you're reducing the resolution. And again, you apply the same operation. You take this as your input, and you apply, in this case, 9 by 9 convolutions, and then you get 256 kernels, right? So it's kind of like you take this feature map, you apply convolutions, you take the next feature map, you apply convolutions, and so forth. So the number of feature maps as you go up kind of shrinks, but grows in size, right? And then people sort of design some techniques to reduce the number of these convolutions. You can average them, or you can drop some of them, and so forth. It's a whole bunch of different methods to do. Yes?
So you just mentioned that we learn the parameters, so does it really matter that we use convolution or correlation?
No, I don't think it matters. You can use correlation. In fact, there are some papers that look at the convolution versus correlation or normalized correlations, and it's the same thing. Because effectively what happens is that traditionally they were called convolution neural networks because this operation was the convolution operation. I think there's been a few papers showing, yeah, instead of convolution you can use correlation, but at the end of the day, it's not like one is better than the other. So, and then you would typically go through the fully connected layer, and then you get your answer. Yes?
So if you want to do like dropout in this setting, since it seems like you're going to be pretty immune to maybe taking like one individual pixel and turning it off with the pooling and everything, would it make more sense to drop out entire filters at a time?
Yeah, it's a good question. I think that when you look at the dropout, the most commonly used technique is to still use the dropout the way it was used, dropping individual hidden units. There's been some work where you're dropping out feature maps. That also helps you regularize. It's not clear one is better than the other. And there's even been a paper that basically drops out the entire layer, right? So there is a lot of, and then there was a paper that was just dropping out connections, like, you know, between I and J, I'm just going to drop out that. It's called drop connect. So people are dropping the whole, you know, a whole bunch of things. And you can imagine, you know, other ways of doing it. It's not like there is one dominant technique. I think the standard dropout is still most commonly used, and they all work about the same. One thing I want to point out is, in many cases, traditional convolutional neural networks would also have a fully connected layer, right? Just connecting everything. And if you think about it, most of the parameters would be sitting here. Right? You have all of these, you know, 256, these are one by one. And if you have, let's say, a fully connected layer of size, you know, 100 or 1,000, then you have 256,000 more features that you're fitting. More recent neural networks, what they do is they just don't have a fully connected layer. They just average, you know, these pooled layers and just basically say it's good enough. So again, in the next class, we're going to look at some of those models that sort of reduce the number of parameters. Yes?
Yeah, in your diagram, you show different size for the pooling and subsampling. Is there any difference between the pooling and subsampling?
Yeah, so pooling is kind of like, I think this was done by Jan LeCun. Generally, they both the same. You know, you pool over the neighborhood and you subsample basically just by that neighborhood. But you can also pool over the larger neighborhood, but use smaller subsampling, like was done in these cases. So it's another hyperparameter that you can tune. Most of the time, it's exactly the same thing. But let me get through the lecture, and then maybe if we have some time at the end of the class, I'll answer more questions. So for classification, so when you're doing classification, your output layer is a regular fully connected layer with softmax nonlinearity. So you have a fully connected layer, and you can put softmax nonlinearity on top of it. The network can be trained by stochastic gradient descent. Backpropagation is exactly the same as in fully connected network, right? It's just the adaptation because your architecture changes. So it's more tedious to implement backpropagation because your parameters are shared across different locations, so you have to maintain that. The only thing that we need to do is we need to be able to pass the gradients through the convolution operation. And again, it's easy, but also from the pooling operation. So for example, if you use max pooling, we have to pass the gradients through the max operation, right? And it turns out that it's actually pretty easy to do. So let L be the loss function. For max pooling, we're pooling over Q by P region. So think of Q being 2 and P being 2, so the 2 by 2 region or 3 by 3 region. And the gradient has this form. So let's look at what the gradient is. The gradient has 0 at all locations except for the winning location, except for the location where the max operation was taking place. So in other words, only the winning units in the layer X get the gradient from the pooled layer, right? So if I'm pooling over 4 by 4, and this unit is the maximum, then I'm only propagating gradient through this unit, and I'm ignoring everything else. So it turns out that it's fairly simple to implement this backpropagation through max operation. For average pooling, if you're trying to do average, it's the same thing, right? Averaging over multiple multiple hidden units, you just compute the gradient, and then you're using upsampling. Upsampling basically means send the same gradient at all locations, right? Because if you averaged over 4 locations, you compute the gradient, you basically send the same gradient at 4 locations. So it's fairly simple to implement both of them. So if you think about using backpropagation for convolutional neural nets, it's the exact same backpropagation algorithm, right? It's just that you have to do a lot of bookkeeping. So writing your own backpropagation for convolutional neural networks is a big pain because you have to maintain that all of these things are shared, parameters are shared, so you have to compute the gradients, but at the same time, it's just a simple calculus, right? And people have designed ways of doing it very efficiently, so you don't have to do it.
Is that assignment 2?
No, that's not going to be assignment 2. That's going to be your midterm question, right? No, just for the record, I'm joking. I'm not going to be asking you to design backpropagation for a convolution operation on the midterm. But nonetheless, this is something that you should be aware of, and for those brave ones, you can actually try to do the convolution. Because in the early 90s, when people looked at these models, they actually had to write their own code. So it's impressive. So the convolutional neural nets, again, you have convolution, you have pooling, convolution, pooling, and so forth. Now, in many cases, people looked at these operations, and it turns out that you can actually need to use other operations so as to improve object recognition. Okay, these basic operations are the basic building blocks, but you need something beyond that. And what that is changes on a year-to-year basis, right? What are the additional things you need to do? One particular thing that people have looked at is rectification layer. So what you do is you just take the absolute values of your feature maps. Okay. So what it can do is it can lose an information whether the edge is black to white or white to black. You're just saying there is an edge. And this is something that sometimes works, sometimes doesn't. So it really depends on the problem that you're trying to solve. There are a few papers that show that that can lead to better recognition of certain objects. In other cases, it does not. Another thing that people looked at is something that's called local contrast normalization, right? So what you do is you take your input, your feature map, and you look at the weighted average of all the activations of in the feature map around your local neighborhood, right? So think of it as basically saying, I want to make sure that the contrast, and this is basically, you can think of it as kind of just putting a Gaussian filter, right? You have a point, you take a little Gaussian filter, and you say normalize it with respect to this small Gaussian filter. So what you want to do is you want to say, I don't want to in one part of the image to have high values and another part of the image to have small values. I want to contrast normalize everything. And this is kind of looks at the local standard deviation. So it reduces UNIS activations if neighbors are also active, right? If I have high value and my neighbors have high values, maybe I should normalize myself, right? To sort of say maybe it's not as important. It also sometimes creates competition between feature maps and scales activations. This is something the local contrast normalization came to us from neuroscience. People have done some studies with monkeys, and apparently our brain can use contrast normalization. So about 7 years ago, when this was published and people have used that, it actually helped a lot in terms of recognition. If you look at existing techniques, like for ImageNet recognition, it turns out it doesn't help. It doesn't hurt, but it doesn't help, right? For some problems, it might help. Maybe for scene recognition, this might help, but for object recognition, it doesn't. But nonetheless, this is what the contrast normalization would look like, right? So here you have, for example, these are different feature maps responding to different kernels or different filters that you've learned. And if you do contrast normalization, this is what the output would look like. So you're doing contrast normalization, you're taking your feature here, you're looking at the weighted average of the features around you, and you do subtraction, and you just normalize everything. So sometimes you see you can kind of like pick up on more patterns, right? Because there's actually some patterns happening here, but because of contrast, some of them appear to be of higher value than others. So you normalize everything. It's almost like standardizing everything to 0, right? So that can help in some cases for some problems. Yes?
About rectification, you mentioned earlier, you said it's not very promising. But isn't it the same as a value activation?
Not quite, because, for example, for the rectification, if you're using sigmoids or if you're using 10H nonlinearities, you can have positive F negative, but the point about local normalization or the rectification is that you rectify pre-activations, right, before they go through the nonlinearity. Yeah. So these are some of the kind of operations that people have looked at. You have some input, you apply these features that you're learning. You can use rectification, you can use contrast normalization, and pooling, and so forth, right? So there's a bunch of different things that people were looking at. So when you're designing your own problem, when you're looking at your own domain, you can try a lot of these different techniques. Rectification or contrast normalization, sometimes it can help, sometimes it doesn't, and so forth. So it's good to know about these things. The last thing that I want to point out is batch normalization, right? This is something that you're doing for your second homework, but batch normalization is actually crucial for training convolutional neural networks. It can help you when you're training fully connected neural nets, but for some reason, it works even better when you're training, when using batch normalization with convolutional neural nets. So this is something to keep in mind, that this has now become kind of a technique that just works uniformly across any convolutional model that you're training, right? So just remember how you would apply this operation. You would apply this operation for every single feature map, right? So for every single feature map, when you're looking at a hidden state, you can normalize the pre-activation so that whatever goes into the hidden unit always has 0 mean variance 1, right? And you can backprop through that. Yes?
So what's the difference between batch normalization and the local contrast normalization?
Good question. Anyone wants to answer? Yes?
Are the batches constructed randomly in batch normalization?
What's constructed randomly?
The batches, like all the training examples in one batch are selected at random.
Sure, yeah.
And here they would be like nearby in some sense.
Yes, that's right. So one of the things to keep in mind is that, first of all, when you do batch normalization, right, you're normalizing the pre-activation, right? So you're normalizing what goes into the hidden unit. You want it to have 0 mean variance 1. But more importantly, you're backpropagating through this operation, which basically you're learning what that normalization should be, and you're also learning the factors, the scaling factors. For contrast normalization, you typically have to pick up the filter size. You say, within my local neighborhood, I want to normalize, right? But this normalization, what it does is it really is saying that I want the value, if the values of hidden units around my neighborhood are high, I want to normalize everyone to be around 0. Right? Batch normalization is not really saying that. Batch normalization is saying whatever the next layer is looking at, whenever its next layer is looking at all of the connected hidden units, and I multiply it by the weights, what goes into the next hidden unit gets normalized. Right? So those two things are different. They are somewhat related, and maybe that's why when batch normalization came online, people no longer use contrast normalization because it doesn't seem to help as much. But yep. Yes.
Can you construct some learnable parameters for contrast normalization?
You can. People have tried doing that. I don't know whether it's been successful or not. The fact that you don't see a lot of papers using it probably means that it doesn't really work as well. Now, in some cases it might work, right? Because here, when you're doing contrast normalization, you're bringing up these new sort of salient features that otherwise might be overshadowed by these more dominant ones, and maybe that's important. Again, I think that it depends on the problems you're trying to solve. Sometimes people use the contrast normalization could be useful, for illumination kind of conditions, right? If I take an image and it was in the dark, so you kind of have more of a grayish features, and then maybe you want to normalize it. Sometimes people look at illumination normalization, and that can help. So depending on what the problem you're trying to solve, this is just one technique for you to make sure that you apply. And then I think that I'm towards the end of the class, so maybe I can just take a couple of questions, because this is fairly an important subject that you should be familiar with. And again, I would encourage you to look at the deep learning book and read the material on convolutional networks. There was a question there, and then I'll take your question. Yeah.
Just make sure that actually the batch normalization isn't average over different instances.
Yes.
So that technique is obviously different from the contrast normalization. Contrast is doing.
That's right. Yes, that's true. But at the same time, yeah, so this one is done over different instances, right? Contrast normalization is more done with respect to your neighbors. But in general, if you're looking at particular detection patterns, one can help another. But for some reason, if you use batch normalization, contrast normalization doesn't really help as much. Contrast normalization helps with optimization as well, because when you're normalizing things, you typically bring everything, the whole input to sort of the same level, right? So you never have part of the input that has high contrast and another part that has low contrast that can affect your optimization. You're bringing everything to the same level. Batch normalization sort of does that, but across different training examples.
Back you showed a picture of the kernel maybe might have been learning edges or something. What is leading to these different feature maps learning different things? Is it just purely the different initialization that we start each one off with?
Yeah, very good question. So why do we actually learn these different filters or these different features? Right, so for example, here we're learning different features. Why are we not learning the same feature? Why is the model discovering these different features? One reason is, first of all, yes, you have to initialize them differently, right? So it's a symmetry breaking. The second thing, remember what we're trying to do here, is we're trying to optimize for classification accuracy, right? If the model is discovering the same repeated feature, then unless unless it results in perfect classification, then it would discover it. But because you're trying to classify so many different things, it has to discover as much as possible, in terms of variability of those features. So it has to find something that's extremely useful for classification. In the next class, we're going to look at some more advanced techniques, and we're going to look at some of the features. But the model is discovering some remarkable things, like, you know, it can discover texture, because it's important for recognizing object. It can discover certain lighting patterns, because again, it's important for classification. So depending on what your task, and that's something that's been holding off a lot of computer vision, because systems like this existed in the 90s, in the 80s. The problem was that nobody was actually successful in terms of training these features from the data. Right, because a lot of these features would look like Gabor-like filters. If you look like little edges and so forth. So people would say, well, why do we need to learn them? We can just embed them in the first layer. Look at the Gabor-like filters and embed them, and then again try to construct. And that's how human visual system works. And those methods were never successful. And it has to do something with the learning, because your objective here is not to find Gabor filters or to find some biologically inspirational features. Your goal of the network is to really classify. I want to classify dogs versus cat. That's it. That's all I want to do. Find me features. Find me these representations, because these are the only tunable parameters that achieve zero training error, right? And by doing that, it's discovering these interesting kinds of features. Again, in the next class, we're going to look at more advanced techniques, and we'll dive a little bit into the architectures, so you have some ideas behind these models before we actually jump into generative models and sort of look at unsupervised learning. Okay, so let's maybe just one more question, and then let's stop. There's a question.
Can convolution deal with features that are scaled up or down?
Can convolution detect features that are scaled upward and downward? What do you mean by upward and downward?
I mean, the size of an object might be large and some imaging is small and so on.
Yes, a good question. Actually, you know, how would you? We're going to look at detection at the next class. But if I have, you know, same object appearing in different sizes, what would you do? Pulling? Scaling?
Yeah, just multiple copies with different sizes.
So we'll talk about in the next class. One simple thing to do, what people have done, is you take an image, right? You take your filter sizes. You take an image, and you basically say, I'm going to run it at scale 255 by 255. Then I'm going to run it at scale 126 by 126, or 128 by 128. Then I'm going to run it at 64 by 64, while the filter sizes remain the same, right? So that's a hack, right? You're kind of like saying, I'm going to look at this image at multiple scales. So things, if it's small, I can detect. If it's large, I can also detect. That's a commonly used practice. More recently, there's been models that basically deal with that just in a single network. You're creating something that's called anchors, which is you're trying to detect small objects and large objects and so forth. So there's a way of solving that. But in general, again, you're looking at the same image at multiple scales. That's basically the idea.